So the devices gets more intelligent. So what is the use of having intelligent machines, intelligent endpoints? Right? It's because we are trying to build the systems. For example, if you looked at Google when it first came, 98, it was still available. But when you search something, you get certain kind of results. But today, when you search, you can type a whole sentence and it will answer your sentence. So things are getting more and more intelligent. And in order to create intelligent system, especially in the controls areas, then you need devices that are a lot more intelligent than simple sensors giving you the temperature and other data. So the way IoT devices have come up is they have CPU, they have memory, they even have some sort of communication mechanisms. And the computation and the data capacity, the amount of information that you can store there, or how fast you can get things out, they are much smaller. So we have to accommodate that. So what are some of the options that we have? Is Arduino is one of the first ones that started, and then we have many different platforms today available. The more popular ones are BeagleBoard, Raspberry Pi. Then on the OS side, you have Zephyr OS and many other customized OS. Linux itself gets very well implemented in some of them, like BeagleBoard. You can load Linux, same as Raspberry Pi. And the boards are also getting cheaper. So if you were looking into some of these at the cost aspect of it, of course, a lot of you know Raspberry Pi anywhere from $25 to $55 and so on. So anybody know what is the price of ESP8266? It still has a microcontroller, and it has it has Wi-Fi and all those things. How much? $2. So this is 8266. So anywhere from less than $2. When you look into the internet, you will see even less than $1. So basically, devices have become cheap. They have become more intelligent, and you can add some software stack into that. So how are we going to make use of it? So the way we communicate, for example, when you run a browser, you are communicating through HTTP. So the high-level protocol has to be well-defined. That's where some of the work early on went into the IoTs. When you have small devices, your network transportation system is restricted. You cannot have a standard MTU like what you send. You cannot send more than 250 or 300 bytes at a time. So when you have these kind of restrictions, you will come up with protocols that will actually suit it. So it has to look somewhat similar to HTTP, but it has to fit into a small frame. So everything has been reduced. Your stack is reduced. The way your session management information, we compare between the HTTP and the couple of protocols that I am going to talk about, you will see that they are made for small devices. So some major ones are MQTT and COAP. These have been pretty popular at device level. MQTT is a message queue type of transportation. It is data agnostic, meaning you will not have data definitions if you had used protobuf and all that. Is or XML, they are well-defined messages that you can create. Whereas here it will more like a string and labels and those kind of things, so much more simpler. But it works for a device that's just going to do a few things and make a decision based on its small environment. You don't really require complicated stuff. But it's how you transport the data. Sometimes you require messaging, sometimes you require more of HTTP-like communication. And when you do that, you go into COAP, which is Constrained Application Protocol. So overall, the IoT environment is a constrained environment. Everything has to fit into those limited resources. So COAP is the lightweight HTTP. There's a lot of information available, but when you think of developing a system, you will have to make sure that your management endpoint at certain point is going to have these kind of protocols. It's not going to be going over normal HTTP. So the cloud, the IoT is of couple of types, right? One is your building automation, industrial IoT, where all these stuff that I was talking about earlier was being used. But if you look at video streaming, for example, augmented reality and virtual reality, and traffic tracking, we are doing some projects where we are able to see there are cameras mounted on multiple automobiles, and you're able to track the environment and then correlate to the static information that we have in the map, and we can predict what is the obstacle going to be. So there are some university projects that we are able to work on around those areas. So the data there is very different. It's not coming through small devices. So you see that there is a range of subsystems, and each one has got different mechanism to communicate, as well as limitations and then requirements. So on the low end, you have IoTs which are having very small data bandwidth and response time, and your overall speed, what you can get done there is much slower than the other end, where you have V2X, where performance is primary. You need near real-time communication and control. So this is where a lot of things are evolving, and where edge becomes absolutely important. So the communication protocol has two types. One is how you send the messages. The other is your medium and how you do the low-level protocol. And there we have 802.15.4. So 802.15.2 is, I think it is Bluetooth, and you had Bluetooth come up as a device networking, but that is still not as lightweight for such small devices. So you have 6LoWPAN. It is primarily based on IPv6. And we'll quickly go over some of these things, because this is where things get more interesting and it gets more technical. Zigbee is quite popular, the Zigbee, and there's also one called OpenThread. Those are in certain category, and then we'll see what other options are available. So when we look into the topology aspect, when you have multiple devices connected, there are some devices are so small. For example, it will be a small sensor in to monitor leaks in a pipeline, which are going to be embedded deep down in the under the earth. You don't want to be changing it so often, and it's not something that it needs to be doing continuous monitoring. I mean, it will monitor continuously, but it doesn't have to keep communicating. So there will be something called sleep mode. So some of these things, they want to extend the battery life as long as the battery can be workable. Like, even if you don't do anything, a battery will lose its power after some time, which is like 5 to 7 years. So if something can stretch until then, that's the kind of requirements we get into. So when you have all these different types of devices, you should be able to address all the topologies. The most common are star and mesh topologies. And in the mesh, for the routing, we have all these OSPF kind of communication. But once you go into IoT devices, it's a lossy network. We call it low power lossy networks. And protocols such as RPL, that is more suited. And then there are a few other variations. So 802.15.4 is actually the low-level protocol, right? Something like Bluetooth, which how it travels through the medium, the link layer, and L1, L2 kind of areas. So on top of that, you have all these Zigbee, Enocean, Sigfox. You also have RPL and all these things. So each one has got different purpose, and it's used in different areas. But in all those protocols, it has to self-organize. That's one of the key things. And it needs to coexist. Of course, these days we have spread spectrum in almost all wireless protocols. A lot of them are wireless, by the way. In fact, the 802.15.4 is a wireless communication protocol. And then protocol must be interoperable. And sometimes you would require it to be interoperable with your standard network. Sometimes you don't have to. So we have all options available. So this is how the generally technologies stack up. Your standard wireless LAN can extend for certain distance, and then your throughput requirements and the cost is where LR, the low power ones, are very cheap, but it has limitations. So this graph tells you how these technologies stack up. So how do they typically get connected? It gets connected through some kind of edge router. So when you do IoT integration, you'll have an edge router which are connected to some router, and then it gets into the internet. This is one way it can be connected. Of course, there are limitations. I'll come to that in a couple of slides. At a high level, this is how the stack looks like. So the stack has, you see the 802.15.4 is at the lowest level, which is the MAC and your transport layer, the medium, how it transfers the data. And Wi-Fi is slightly different, and then OSI model out here. This kind of illustrates, this picture illustrates how you can extend or how you design your topologies. So I was saying that in some cases you require much lower powered and more isolated networks. So the bottom one is called mesh under. It doesn't really go into the transport layer. If you see when you chain the devices together, it actually doesn't go up the higher level. So an example of that is OpenThread. Same thing with Zigbee. In those things, all of them are IPv6 based, because your 802.14.4 is kind of a IPv6 base. So you do some manipulation how you create your addresses, and that's how it actually when it is doing multiple hops, it doesn't go up to the network layer. It can actually keep getting transmitted across based on protocol defined at a lower layer. Whereas RPL, you go into the network layer. What is the advantage? Obviously, when you are manipulating the IPv6, the 128-bit, you allocate certain bits for doing certain things. That's going to hit a limit. So you'll have something like 500 devices you can have in per high-level router, those kind of limitations. So RPL doesn't have that. It's much more, because it's going up the network layer. You really can have as many as you want. So how generally the mesh topologies work is something like this. The nomenclature varies differently when you go from RPL to Zigbee to OpenThread, but all of them have similar concepts. You use what is called as a directed acyclic graph. Acyclic because you shouldn't have any loops. So the RPL and certain other protocols, they have mechanisms. Like they have a direction bit. When the command goes southbound, then it has a particular bit, is 0 or 1. And when it goes up, it is different. Yeah.
So the leaf nodes is the IoT device here, is it?
Any of them can be IoT device.
The end device.
Yeah, so I'll explain just in a moment. So basically, because they are all low power devices and the range is very restricted, you have, it is imperative that it's going to hop across. So if you have a device here and then a device at the end of that wall, this device doesn't have more than 20 feet of distance. So it's going to talk to that device, and that device will relay the information. So any device that relays the message is the intermediate ones that have set as RFD, which is the restricted function device that has routing capabilities. So in OpenThread it is called routable and some other nomenclature that it goes by. So typically when you have a directed acyclic graph, you have a common route. So the message always goes towards a particular route. And in RPL it is called direction-oriented DAG. So DO-DAG is what is called there, because the messages always travel upwards towards a destination. And in these cases, each of these bubble can be a device. Typically, the topmost root node will be a router that is typically called a gateway, and that's what interfaces with the external world. And then coming down, this can be a device. Suppose it is able to connect to a available electrical outlet. It can do transmit and respond. But if it is going to be in a remote place with a battery operated, then it may be able to do a routing function, but it need not. So more extension to this graph is, for example, you come to this place and you can have 10 different nodes going out of it. So you'll have a star topology connected in a graph. So the end device is typically a leaf device that doesn't do a relay, or the least that has the least power capacity. So you create this topology in an IoT subsystem based on these requirements of how much power is available and what kind of bandwidths you have. And of course, the cycles, there are various ways to not have the circular loop going into that. So RPL, the way it works is you have messages like DIO and DAO. So the root node will always be transmitting the DIO, and once one of the lower the devices in the lower in the graph, they will respond to the DIO message, and then they will be able to request if they can get added to that. And along with this message, you also have what is called as ranking. So if there are multiple paths to a particular node, then depending on the rank, it will be able to choose which of the two nodes that it has to use as a path towards the route. So that path selection is critical. It is defined in the protocol in RPL. So it automatically gets adjusted at any time, taking the shortest path, which is why destination oriented means it is a distance vector protocol. So it will always balance itself by going through the shortest path. The root node, each root node creates a DAG graph. There could be multiple ones. You will have a similar topology also available in OpenThread, where they call it as partitions. So in one partition will not be able to talk to other partition, but the moment there is some kind of a link, they will be able to balance itself. It will redraw the DAG, and then it will all become a single partition. Whereas in RPL, you keep them separate, and if you have to merge any of the two DAGs, then there are some changes. Because in RPL, what happens is the root node will have the main IPv6 address, which is what is connected to rest of the network. And then rest of the nodes under it will all have the same prefix but different addresses. So you won't directly be able to, you'll be able to address every node, But once you move a particular node from one DAG route to the other, then its prefix is going to change. So it has to it has to change the IP address. So there are some issues like this you have to take care of.
Question?
Yeah.
Instead of a tree structure, the branching structure, would it not be ideal to have a hub and spoke configuration where hub-to-hub connection could be there, and the spoke is the one which goes and connects to the IoT? That would be more efficient in terms of routing, in terms of survivability for any disasters or failures, and so on.
So there are a couple of points. One is they are wireless systems. Most of these are wireless. So you can have subsystems which are connected in different topologies. Eventually it comes down to what fits the environment and what is most optimal. There is no single so when you have a mesh configuration, these are the options. Now if you think your star and hub topology works better, of course, but a lot of times when you integrate everything together, you will see that the mesh gives you a lot more flexibility, because you can manage your endpoints much more efficiently.
And for activations, not only collecting information.
Say again?
Even in addition to sensing or collecting information, go to a central processor, even for actuators, in a manufacturing environment and otherwise.
Yeah. So all these nodes are intelligent devices. You need to make a distinction there, because they have their own processor. They're able to do certain things on their own, and the control configuration is through the messages or commands. So it's almost like miniature computers sitting all across, and then how they are communicating with each other. I spent some time on this RPL because it was required in certain configuration. So you have a lot of protocols, many technologies. If you you know, 6LoWPAN edge router that's connected to rest of the routers. What if I am having a thread? Because when you do IoT, things change. Some configurations will have some technology, some other technologies are to be introduced in others. So it is important to have a common platform, and that is where you will get into what is called as federated learning systems and edge cloud. So edge cloud is not like there is one edge and you are communicating with some other cloud. So just this is the edge. So the way it is evolving is that at every level you are trying to consolidate information. Because if you are sending all these information from billions of devices up into the cloud, you require a really huge bandwidth. You don't want to do that. And also the traffic congestion and other things will prevent you from doing that. So you start doing a lot of in-place computation. And what helps in place is that at every level where you have more intelligent cloud kind of environment, that's going to report to its higher level cloud environment. And that builds up, you can imagine there's going to be a graph of clouds. That's where it is evolving. There is a very good talk at ELC. It was by I forgot the name of the person, Patricia something. She's from EMC, and this whole talk is about federated analytics. It's about how the data is exploding at the edges, and then you can't really take everything into the cloud and then keep processing it, but rather you start processing at edges. So we are working on multiple projects on how you build AI data models which will actually span across the cloud, where you do certain kind of determinations and only pass some of the results. It's a very complicated field, and this requires you to have a good view of how the devices are laid out, how the network is laid out, and then what information you can get at different places. Eventually, it's the information that is critical, right? It's not your network or it's not your IoT device. It's what intelligence you're obtaining from that. And when we start focusing on that, what you will come up with is a much more sophisticated system, where you will have edge cloud that hooks into IoT kind of a mesh. It can get into also VTX infrastructure, and everything is interconnected. It's a connected world, and there are challenges at every level. At the moment, we are looking into edge cloud, and also trying to see when we have to do federated computing, how are we going to manage the WAN. So SD-WAN is playing into this aspect also. And also the network slicing is a big thing, because you saw how the devices are much slower than certain other kinds of communication, and edge cloud should provide those kind of guarantees that when you require a 1 microsecond round trip latency, you get 1 microsecond because if you don't achieve that kind of latency, then that message is useless. A lot of times an event would have passed. If your car is traveling and it's finding an obstruction, and within 2 microseconds you have to tell the car to stop. If you don't, it's going to hit that. So after that, if you send a response, it's of no use. So quality of service, your SLAs and your guarantees and service guarantees, how the system gets designed becomes more important. So you're seeing evolution of real-time operating systems and hypervisors for real-time system. So ACON is another big project that also is sponsored by Intel, as well as you have the real-time Zephyr OS. RPL is available on Zephyr, and you have ACON, which is freely available. There's just a lot of technology. I can go on talking, but I'm already out of time. So if there are any quick questions, we can get into that.
Time you could not get into the details of the federated learning.
Yes.
What are the machine learning aspects of it that would be there? And then a lot of times you probably need to have scaled machine learning depending on the environment, how much traffic is coming in, how quickly you have to make the decisions, and so on. And is there any pointers that you can give us? If we want to go into details, you want to see the smart city, smart airport, etc., public cloud connected to that. How does the knowledge go back and forth in the federated learning?
Well, in federated learning, it's mainly your inferences is what travels. Most of the computation is done in place, and your determination is also done in place. There are different ML models you run on the edge as well as the cloud. I don't work on the AI side that much as looking into what is needed in the infrastructure. So in the infrastructure, some of the things that are needed are you require low bandwidth communication, as well as you require high data connectivity. So if you are aware of how the systems work, suppose you get a T1 line, you are not going to get a very powerful T1 line. You probably get a 1 GB line or something like that. But you have to transport tons of data for video communications. And you can't send everything. So what you do is end up doing data partition. You create shards at the edge, and you do pre-processing at the edge. And then the inferences may not be as a result of something, but it will reduce the amount of data that is generated at the edge. So that data has to be transported into the main cloud. At that time, if you're sending through single links, then it will max the bandwidth. For example, if you had a 25 GB link, that's going to fill up in no time. Whereas if you had multiple links like that, then what are the technologies that are required to do that? So those are the areas where the research is happening right now. How you can, send the data which is larger than the pipeline available, and how are the inferences made. So there are too many levers here. So there's no single answer how it is done.
The thing is, ML is not a singular, it's a plural.
Yeah.
There are many kinds of, many types of ML languages that would be coming up over time, learning models. What you get is not the inference, you get the model of whatever the environment that you are doing the machine learning about, and the kind of language, machine learning tools that you use depends on what type of, what is a black box that you are using or a white box approach you are using, rather than inference based in a paradigm I'm talking.
Yeah. It's not inference, it will be reduced data. It's more like map reduce kind of scenario. Yeah. Yeah. Yeah.
Okay, those are.
Sure. Sure. Anything else? All right. Thank you.
Thank you, Murli. That was an enlightening talk. Now I'll invite Uri to come on stage. So he'll talk about, are the first machine learning applications for network the most lucrative? He's the CTO for Data Center Networking Solutions Group at Intel's Data Center Group. In this role, he is responsible for creating networking-related technical strategy for various market segments like cloud, telco, and enterprise. His work includes open source top-to-bottom stack architectures. During the last few years, Uri has focused on SDN and FV and also represented Intel as VC architecture for the OpenO MANO community, IETF NSH co-editor, OpenStack, ODL, TSC, and board, and has worked on vSwitch and influences the server platforms. He's a networking specialist with more than 25 years of industry experience and has a proven track record of creating innovative product architectures, strategies, and in networking, virtualization, security, etc. So with that, I'll give the stage to Uri. Looks like we're just hooking up the laptop. So in the meantime, I'll just give a little bit of housekeeping. So in the end, we'll have some fun prizes, so stay. Those of you who registered at C events, there will be prizes for those who are present. Also, there will be some prizes. And there will be a fun activity called Idea Relay at the end. So looks like we're good to go. Uri? Thank you.
Okay. Evening, everybody. Thanks for sharing your evening with us. This talk is slightly modified version of a talk that was delivered last month at the Open Networking Summit. I have updated it a little bit. It has, as you could see from the cover, it has a few people that are involved here. Very proud to work with John Strassner on, some of you may know him from the IETF. He's very well known for his work on policies. This work is also covering some of work we are doing jointly with others whose name you could see at the bottom as part of ETSI. ETSI has a work group called Experiential Network Intelligence. That group is attempting to create a framework. I'm not using exactly the word standard, even though it is going to be a standard, around machine learning and its application for telco specifically. We'll touch a little bit about their work as well. And so without further ado, let's actually talk about some of those visionaries that more than 2 generations ago, maybe some of the folks in the room here were not even walking the planet yet, were already asking for some resources to be set aside in order to start what we these days refer to machine learning. That is to say that machine learning, or more specifically artificial intelligence, has been around for some time. What is changing recently is the fact that because of the evolution of platforms, compute, storage, open source, then and other technologies like that are related to big data, Hadoop, and what have you, what happens is that this becomes more democratized and is available for everybody and for many use cases. So indeed, we are going to talk about different use cases. We are going to talk about some basic aspects of architecture that are needed in order to pull it off the ground, some challenges that the industry has in order to get there, and some basic insights into what the architecture has and what challenges we have to overcome. And obviously, as the title of the talk has suggested, what are the applications? What can we do? How do we all become successful? So one of, just to give a very brief touch of marketing here, one of the key questions everybody wants, so is that a major area or is that not a major area? So just to give you a few numbers, in 2017, the industry spent a little bit more than $19 billion on this area. This represents a growth of 54% over the previous year. By the year 2021, the expectation is that as an industry, we'll spend $52 billion, meaning that represents a CAGR of 40-some%. So that absolutely is an area of interest, and if you're spending your time over there, you're not wasting your time. However, today, and we'll look at some use cases where Telco is using the big operators, what kind of services they are providing today, and you'll see that significant investment goes in the direction of user-facing versus network-facing. Significant investment goes in enterprise versus telco, so there is a significant opportunity to untap over there. That slide should raise some eyebrows. Is he talking about machine learning, or is he talking about application on infrastructure? What's going on over here? So I'll let this question hang up in the air a little bit, and you'll see how it comes to a resolution, hopefully. So everybody knows the original application model, like maybe 15 years ago. You have some application, it's intimately tied to the drivers, to the operating system, to the platform. Then we morphed to virtualization for multiple reasons, and if somebody would have question, if we have time, I'm happy, because I can present just this slide for 30 minutes, which we're not going to do here. But what happens is that you start, as you could see those red brackets, the application starts to lift off from the infrastructure. We have para-virtualized drivers and so on and so forth. As we move to the right side to containers, which is the next phase, we see multiple phases or multiple types of container-based applications. There is one audacious title that I'm hanging on top of that, and that is microservices. Why am I doing that? I'm doing that for one reason. I'm claiming that one of the major differences that we are going to see as we are evolving to the right side of this diagram is that applications are broken into more and more pieces. Application broken into more pieces means more communication between the pieces. It means also, if you go all the way to the right, like function as a service, you are talking about stuff that is ephemeral, that lives much shorter. The latency requirements are actually going more stringent. The latency tail is becoming very important. You are now dealing with a system that is more complicated to operate. If I had a mail server and it was on one physical machine, maybe it could serve so many hundred users. I need to buy another one to serve the next batch of some hundreds. But if I have trouble, I go to that machine. Now my application is broken into many, many pieces. So I have a little bit of a butterfly effect. What happens if some event happens on the right side of the data center while the effect is felt on the left side of the data center? What happens if I'm looking at the application from the outside? I'm just a user, and now I'm trying to understand, okay, the SLA just dropped on me. I'm an operator. I need to service that user. What piece is required? What piece has actually caused that effect? So it goes both ways. I want to be in a situation that I can say this component of the application contributes that much to the total of the application behavior, but I also need to go the other way around. This becomes rather complicated, rather fast. So maybe we have some interesting opportunity over here. Maybe what we have is, and we all know that Telco is not exactly there yet in terms of containers. It's really someplace in virtualization right now with all the work we are doing in MANO as an example, and the whole network function virtualization that Sujata was introducing to you earlier. So maybe there is a need, but maybe there is also technology that is right here around the corner to go solve that need. Maybe the combination of some machine learning with that growing complexity of the application, with the growing latencies and pieces of workload moving right and left, etc., is creating an opportunity not only on the technical front, but also on something else that is really important for Telco, which is reducing the cost of running your network, reducing the OpEx. So if we go and look at the left side, let us look at management patterns or the way people are managing network. We see that poor human almost strangled in the network cable over there. And the way many places are really running today is that you could see this is the ITIL cycle. There is planning, etc. Now let's say I have a problem. Somebody is monitoring something. A ticket is being issued. The human gets involved. And we all know that cycle. Not only the planning, adding some new equipment, etc., takes many weeks, if not more. Troubleshooting when a human is involved, when we are faced with these ever-shrinking time budgets for applications, containers are short-lived, the user interaction with our network is short-lived, etc., that model doesn't really work any longer. So what we would like to see is a model that is more on the right side, where things are really becoming way more automatic, where if a problem is there, it is being detected. Actually, ideally, I'd love the problem to be detected before it manifests itself in a way that deteriorates the SLA I exposed to a user. So that is really nice, but how does that happen? And just to add a little bit more injury on insult here, some cases the user is going to be the first to feel that your network is slowing down. So to some users, to some application, slow is the new down. They would not really like something that is going to be slow. And if you look at what tools are doing today for us, you could get some SNMP. It's going to take you so much work to go there. You could get some syslog that is going to tell you, oh, this CPU is heating up, or oh, I'll issue an alert, and that alert would be in 240 seconds. I'll shut down this CPU. That is really nice, but why is this happening? And what can I do about that? And can I get some predictive action to take care of that? So these are the set of challenges that we have. The distributed application, the fact that we are fundamentally sitting on shared infrastructure. We are not only sitting on shared infrastructure, there are multiple elements that contribute to the application. They come from different schools, they come from different tools, they use different mechanisms to control them, they present different telemetry data. It is a huge hodgepodge that we need to manage. How do we manage that? How do we correlate that? Some management platforms today would give you a graph. It's going to show you some CPU utilization, and then there's going to be some spike. And if you want to know what happened with the storage, oh, there's going to be another graph. And a human needs to correlate those graphs. That doesn't scale. That doesn't make sense. And it anyhow behind what has already happened. If we even look, and maybe the last point before we look at the graph is that I actually would like to also have policy and business logic integrated here, because this is not about treating everybody and every application in the same exact way. This is really about optimizing what we do for the right outcome for the business. Well, many network protocols and tools are not even aware of that. If we even look at something as basic, let's imagine that at the bottom right is your CPU utilization. And clearly, or your network utilization, doesn't matter. And you need to monitor that to understand what's going on. But you have a relatively weak CPU. If people here are familiar with what's going on telemetry streaming, on like physical switches, etc. Or you, for operational reasons, what are you going to do with all of this data? So what you do, you actually sample it at some rate. Let's say this was your rate, this red thing. What is happening is you just missed some useful information. You simply didn't sample in the right time. You missed some of those spikes. So there are multiple things that we would need to do here. We need to make sure that all of these information that we are collecting from the different aspects of our infrastructure are actually coordinated. As we are seeing higher and higher adoption of network function virtualization, the server becomes another element of shared infrastructure. We need its help in order to help with isolation. We need real-time resolution under SLA. Let's see what machine learning can do for us. And we obviously have this problem and question of what happens with the very different areas that we get machine learning. Now, another thing is happening while all of that is our problem, and that is a big wave of data is washing to our shores. And you could see that what happens is that in just 2 years from now, if a user, these are us humans, before the average was 650 megabytes, this is more than doubling to 1.5. We are seeing all of those other phenomena showing up, and on top of that, and Murli just mentioned some aspects of IoT and 5G, and just to give you some nice number, 50 billion devices in 2021, 212 billion sensors. We are talking significant problem over here. All of those devices really are depending on some response time, some real time, etc. Okay. So how are we going to deal with it? Let's start looking at some of the architectural components. Clearly not lost on anyone here is that we are going to have to do something on big data. So few V's for you to remember, and none of them represent any victory. So you need to deal with the data at rest. We talked about the ever-shrinking time base, so the data is moving much faster, multiple sources. It also changes very fast, which really means one of the fundamental things I want to do for machine learning is data cleansing, and also being able to verify that the data I'm using is data that could be trusted for the purpose. We all know what happens with data on social networks. Here we are dealing with data that is supposed to provide some services. So what data can I trust? But at the same time, I'm also getting pinged from another direction, because the time I have to do that is shrinking more and more. So we have some problems with this big data, and we need to optimize the time in order to achieve whatever level of performance we care about. We need to make sure that the performance for whatever is our product or our environment, we need to make sure that we invest properly in the computational efforts. But then we'll find some forces that are not going to necessarily cooperate with us. So viscosity here, a borrowed term, is really about, I have all of this data, I need to turn the data into some insights. That takes effort, it takes time, it takes compute. Well, those problems of the volume and the speed of the data are going to work against me. The questions of is the data going to be ready to be visualized by a human, or do I need now data scientist that is attached to every petabyte of data, and so on. And where is the value? And to simply drive another aspect of the challenges with big data home, the problem is also borrowing Parkinson law that said, you know, that people are going to do as much work as the time that they are given is going to allow. Here with big data, the problem could be that we are going to gobble up as much data as our storage capacity is going to allow us, but it doesn't mean that we are collecting the right data. It doesn't mean that we really want to always go over all of that data, or that we are even know what is it that we need to collect. So we'll come back to that notion in a second. If we are looking, and that's what I was hinting at the beginning of this talk, to the evolution of artificial intelligence and machine learning, as we discussed, this has been around for a long, long time. It's not that it's being invented right now. But where we are as an industry is pretty much on the bottom left side here. So many times what you find is, I can actually talk about what has happened. If I'm lucky, I would also generate some insights into why this was happening. Where we want to go is we want to go to the upper echelon of using those new technologies, because what we want to start doing is we want to start getting to the predictive phase. I want to be in a situation that I can tell what is going to happen, why is that going to happen, and if I'm really successful, I want to get to cognition. There are many names for this. I'm not going to bore you, risking you're really going to fall asleep with all of the alphabetic soup of machine learning, many different models people have. So like as an example, the DIKW, for those of you familiar, the OODA loop, etc. Not getting into this right now. What we are trying to do is to get to cognition. We are trying to get to the situation that our system could, as closely as possible and as reasonable from business return, mimic a human behavior in its ability to reason, understand, make decisions, and we'll see a basic architecture which is theoretic for a system like that. If you want, by 2020, 40% of the enterprises' new investment would be in this area, as IDC predicts, in those areas of predictive analytics and prescriptive. Prescriptive really means my system is now not only able to predict what happens, but it sees these 4 different paths for the business to progress, and it is going to recommend which one you may want to take. Okay, if we want to hone it on a little bit to the telco, to the networks, we could look at some really nice things that we don't have today that would be really nice to have. I'd like to solve the problem of ingestion, because it's coming from different tools. In each, even in a single stack, you'll get different tools. How do we do this? We are using in machine learning, we need to normalize that. So we talked about the big data, the need to cleanse the data. We also need to normalize that, and that is another borrowed term, ontology, where we agree on a normative way to describe entities, their types, their attributes, as well as the interrelationship between them. When I have that tool in my pocket, now I could really turn to programmatic ways to compare between data collected here to data collected there, because I can abstract them and bring them to one common representation that computer languages could really interpret. I want to understand, and I need to coordinate the information I get from what I just configured the system to do with all of the different aspects of what we refer to as infrastructure. Because if I only get insights from one area, it's probably not going to give me the complete picture. I'm not going to be able to know how to optimize or what just happened. And I think the rest of it is straightforward. Another example at the bottom is, if I'm really lucky, I could start doing some sort of a what-if analysis. What actually is going to happen if this failure is going to affect me this place, and now what is my blast zone, what is the impact it's going to take, etc. So if we look at the richness of technology that, or problems or opportunities that we have in the telco space, there are many, many examples on this slide as to in what areas we have pain and in what areas we could go employ these technologies in order to address them. It's suffice to just talk about the 4 that I highlight on the upper left portion of that slide. Go solve any of them. It's going to be really wonderful. One thing to actually notice, and now we'll double click and see some examples of what's happening in the industry. One thing to notice is that we are not just talking OpEx. We're talking top line as well. We're talking about opportunities that come from my ability to use this technology in order to increase revenue. And indeed, what's going to happen when we talk about some of, especially US carriers that are public with their efforts, we'll see that what they are doing has to first deal with the customer, make sure nobody beats them over there, and only then they're going to go to the network. But I actually, just in the order of the slides I have here, this slide represents actually data collected from the folks you see at the bottom. These are all people who are operating hyperscale infrastructure. And I happened to participate on a panel at OFC in March with some folks from these companies, and this is one of the main sources for the data that I'm showing on this slide. So this is kind of their feedback. These are all people who are using already some level of machine learning in their environment, and they are saying, here is our takeaway from our experience in the last few years. The number one issue they bring up is, oh, if I have garbage in, I have garbage out. Give me trusted data. I'm not in that situation. As an example, the Microsoft example showing on the bottom right side, they were using artificial intelligence in order to help themselves manage the significant fiber optic networks that they deploy in East Asia. According to them, some area in Japan and in the Philippines is very sensitive to cables being torn down. And obviously they don't want to disrupt the service. So they always are trying to use algorithms in order to figure out how to route the traffic. Problem is that some devices don't give them even the right data. What devices do they trust? How do they even tell they could trust the device, and so on? We talked about the telemetry streaming. I touched on that very briefly. Multiple efforts in the industry. Those of you who are closer to that, stuff like OpenConfig, S-Flow, etc. The importance of this is about changing the way I collect data. This goes back to our big data problem. Don't inundate me with all of those numbers. I honestly couldn't care less. Give me the data that I need. Now, specifically as an operator, I believe that the problem I'm going to have, or the problem I'm troubleshooting, is about this. I'll give you a profile to a device. The device should give me exactly that information back. When that event happens, let me know. Otherwise, keep your peace and don't give me data I don't need. We talked about the different vendors. We talked about the problem that data deluge means you are wasting my cycles. As a matter of fact, there was a numerical example given that you are going to, if you're simply collecting everything, you're going to have a larger data center than your data center just to process. So obviously you don't want to go in that direction. The problem or the right tool, this is to say not every problem can be, should be, not every workload is adequate for whatever type of machine learning technology you want to use. And indeed, in many cases, people don't use that, but something that is rule-based is good enough. Centralized control is clear. The last point here is about hey, even on something as benign as alerts, if I want to create my alert for my network, I had a long cycle. Now I could have something much shorter. This is a busy slide. We'll have a few more slides of examples, and then we'll go deeper into architecture and the work that is happening in ENI right now. Some examples here. One example that I find kind of at least exciting, it definitely looks very good, is the upper right side. This is AT&T using unmanned aircraft devices to actually go from one antenna tower to the other to figure out what of the device is rusting or if there is any damage for whatever reason. And only based on this, we are going to send a field crew over there to actually look at that. This is using computer vision. This is using machine learning to understand what we have just looked at. And one of the other aspects is not just cost saving, but also safety for the team. But this is just something that looks nice. They also have a platform. It's an open standard, works in the context of ONUP, and some people in the room here are active in ONUP, as I can see on the right side, or at least my right side. And then Akumus is a platform for you to check in your algorithm. Has some challenges, has some opportunities, not going to go into this. For their own network, they are talking about 3 phases. First phase, they are simply going to do speech recognition, again, user-facing. The second phase is going to be to really work on the network. And the third phase is going to be go to IoT big data. Apparently, they believe they still have some time for that market. But as you could see, they're using AI for other reasons. Verizon could not obviously allow themselves to be behind, so they have a platform that they called Exponent, and that platform is really an offering they have for a secondary operators, so they could use the Verizon provided algorithms as well as many other tools, a full environment to go build their own solution. Much like other that we have here on the list, they want to change the maintenance to be condition-based. Instead of sending a crew down every 6 months to do X, let me actually send them only when the condition requires that. And if you have fuzzy logic in your engine in your car, you're using something similar. Many examples here. I'm not going to spend all the time on this because I want to make sure we have some time for fun technology stuff. Just to show you, many of the examples here are about chatbots that are being put in front of a customer. Everybody who's calling on a service provider is probably hitting those. Some experiments with self-organizing networks in order to improve signal quality, in order to improve drop time, in order to improve capacity planning, and so on and so forth. ENI that I mentioned before has multiple use cases. Those use cases are being contributed by the respective operators, which makes it nice. Not all use cases are going to call on some real deep learning or even machine learning. Some of them don't really go that far, but we'll have a meeting next month. One of the very promising aspects is going to be collaboration with 5G on network slicing, something called Monarch, where the complexity definitely represents and justifies something where machine learning and the architecture I'm going to show you is justified. If you're interested in the rough schedule, here is the rough schedule, standard organization. Some of those documents are already public. Some quick examples. So we talked about the intelligent network slicing. The aspects to deal with here is to help make a choice. What slice am I going to use? Even intra-slice resource allocation. How is this working? Does it really meet my SLA, etc.? Many opportunities to work here. Another example, very visual, I find it to be, is if you look at those graphs at the bottom, the 3 colors over there, we are looking at 3 services with whatever changing bandwidth requirement or resource consumption, doesn't matter. You could think of it as competition that happens within one slice of the 5G network. And as you could see, the top, that yellow orangey line on the top represents the cumulative request for resources. Well, at some point we are going to hit a peak and somebody is going to have to give up. We would like to, as one of the arrows over there, I don't have a pointer here, suggest we would like to know that in advance, and then we would like to change the policy such that in this case, number 2 is going to give up some bandwidth because number 1 is higher business priority or paid more, whatever, and so we are going to keep that service for that guy. a different look at the different applications that are available. And again, this slide could be presented by itself for a long time, is what different vendors are doing. If we are categorizing that roughly, starting from the middle, since I happen to work for Intel, there is work that we are doing. As an example, I would call it the foundational work, where we create platforms that could do better job on training as well as on inference. If you look at the upper right side and at the bottom left side, you'll find Cisco, Huawei saying, let me use the network devices that I have in order to infer from them what is going on in the data center. The bottom left side is a system called Ulzer. That is a system that could handle million signals a second in a data center. Going to cost you seven digits as well. Going to consume 35K watts. It is a large system. And going back to our discussion about big data and data deluge, you could say, is that going to solve my problem? Do I need something different? Not to suggest by any stretch of imagination it doesn't have value. The question is, what are you trying to solve? And we talked about the platform, so again, I'm going to save some time here. If we try to refer our new tool, this machine learning, to the ETSI MANO model, anyone in the room doesn't know this, need me to walk through what that is? Raise your hand. Okay, this is after all Silicon Valley, no problem. So the question is, where should I place my little machine learning intelligence? And you could see the work I'm involved with at ETSI has to do with putting that on top of a MANO. Some people, as we alluded to, number 4, go put it on a network device. Number 3, go put it on really where the user is. I want to understand who's watching what movie, does he or she have the right experience, etc. Number 2 says, oh, let me put it closer to the infrastructure, because as you could see on the left side, there is a difference between 1 and 2. 1 really represents the full cycle of machine learning, while 2 represents some shortcut. The shortcut is going to help us on 2 aspects. It's going to help us on the real timeliness, because if I'm placing my stuff as number 1, I am going to lose real-time aspects. I'm also going to deal with lots of data. Can I cut back on that data? So that's something to think about. Another little problem with our network. The problem is that we do not actually have any agreement, not only on APIs and on stacks, we don't also have a model for the network itself. If we say that what we need to do is cleanse the data, then we need to normalize it somehow, what is the way I actually deal with my network? So here is a proposal that some people are looking into. That is one of the areas of machine learning. And this, sorry, my machine is saying not enough time, you should move faster. This is about a reward system. This is about an approach to machine learning. As you could see at the bottom, I'll do the mathematical representation, and hopefully that's going to help you. So the way you determine the next state at t+1 is based on the reward you got at the previous time slot, and that has to do with the state and the action that you took in the previous time slot. But the key point here, I'm not trying to algorithmically nail it. I'm actually trying to not use an exact mathematical model to represent what I'm trying to do. I'm actually trying to use this reward in order to incrementally close the loop on where I'm trying to go. And And the Vega stuff at the bottom this is modeled after what's called a multi-arm bandit. Imagine you're in Vegas and not here right now, and you're trying to solve the problem of I have all of those machines, which one should I use for how long? It's not necessarily a case where you have a mathematical model. Another component that we need before we could get to our architecture work is to start integrating policy into this whole scheme. Personally, was involved with multiple efforts in the IETF as well as other organizations. John is definitely one of the guys who are leading that. One of the things that we believe is needed, if you think about basically the different types of policy, imperative, declarative, and intent, where imperative is really the how, declarative is the what. I expect this to happen. I'm not going to tell you how. You translate that to whatever set of commands to your devices. With intent, we are saying this is even one step more remote. The reason is we need to use, again, this something that other aspects of my system can work with. So it needs to be something that is close to natural language, so the data I collect could work with the policy could work with the data, I could morph them. So I need to abstract it one level higher. So the difference between that and declarative would be that I may need to have another mapping step before I could use that. So here is work that was going on in the industry some time ago. Here are the different blocks. There is a paper we'll touch on in the next minute or so. And these are all the phases of your infrastructure. This whole machine is really getting into effect when your context is set, meaning you really know what environment you're working on. Before you have that, you cannot take action. So if your environment is that a user outside of my organization should not have access to this data, then there is no point on working on giving him access. The problem with this, exactly like the slide I showed you before, this is a long loop. This takes a long time. So we have an optimization coming up that is more real-time oriented. All of this is machine learning controlled. The paper that was published back a decade ago has that name. If simply, as we are running out of time, can we go longer, like 2 minutes or so? Or, yeah, okay. So what you see here in those elements is that we start with the context manager, that context that actually tells us what is really the environment that we are working on. And then based on this, we are going to select a set of policies because the policies I need to use have to understand the context I'm really working on. That's going to feed into the autonomic manager, and then that manager is really controlling the heart of this whole apparatus. In the heart of this, we are really trying to understand whether the state the machine is at is really the state that I wanted it to be. Does it match my intent? If it does, we are done. If not, then I need to consult those that on this diagram looks like the support at the bottom. I need to use those in order to help me understand how do I change the state of the machine. And when I change the state of the machine, I'm going to issue new policies. The machine is going to react. The other thing I need to do is also to update the policies that collect the telemetry from that machine, because now I'm actually looking at a different state, potentially also changing what I need to collect from that environment. Another thing that after working with multiple MANO communities, I find very compelling if we as an industry could simply get there one day, is that notion of model-driven top to bottom. That was introduced some time ago, and as an industry, we are struggling with that a lot. To do justice to this in half a minute here, it starts from some ability to represent the business policy that you want to achieve. The problem is that, as you see, there are multiple data models, different devices work with different standards, and so what I really am striving to achieve is one common information model, and then using some abstraction layers to translate that to whatever the devices are going to have. It's the same theme of I need common ground in order to achieve my goal. This is the work will be done in a minute. This is the architecture that we are working on ETSI. It's a different representation of the graph of the diagram you saw before. You could notice here knowledge representation, which is that normalization of the data I was talking about. It has other elements like situational awareness. In other words, if you don't understand the system good enough, you're going to issue a command that may deteriorate the state rather than improve it. So it's not only the context, you need to have the situation as well. And we talked about what cognition means. It could have two modes, by the way. One mode is assistive, where it could issue some recommendation, take it or leave it. Another one is that it really controls the system that you see on the left. Just FYI, many other efforts to follow. We as Intel are working on many, many aspects here. And to bring it to a close, so what have we covered? So in order for us to achieve an architecture, we need all of these components. We need policies, we need data aggregations, we need to agree on presentation formats, we need to minimize the telemetry we are collecting, we need to agree on the algorithms and the platforms that are going to help the industry move forward. I'm suggesting we also consider what I call distributed telemetry intelligence. In other words, be aware of what you are collecting given the business problem or the technical challenge you're trying to solve. Don't collect everything because you're really wasting resources. There are ways to do that. We talked about the role ETSI plays and that engine that they are defining, as well as reference points that is going to help the whole industry come together between all of those organizations who are working on this. Clearly, if you want to turn data from zeros and ones to value, we need to have that. And then, obviously, there was the question of what are the applications? Where's the money? So I want to give you a few examples. One is this whole 5G transition. We talked about the application lifecycle. We talked about the new challenges and the opportunity for machine learning to solve that. Same is true for just general container or cloud native, and everybody is looking for operational efficiencies. So probably in a few years we'll have some better examples, but that's all I have for you tonight. Thank you. Sorry it took a few more minutes.
So I have a question.
Oh, yeah.
So on the data collection front, is there work happening for network collection?
What do you mean?
So AI depends on data collection, right? So how do we collect data? Do we collect data on real networks?
So it's a good question. I think at this point, at least from the work I'm aware of, I have not yet seen any significant work that goes about how to reduce the data. We are still at the point of people are trying to even put all of those planets in some sort of a constellation and just have the loop closed. Optimizations on collecting the data. Right now you have data from myriad types of sources, and they all talk different languages. If you are trying to sell a network switch today that doesn't have SNMP, you're going to have trouble. if you are trying to use SNMP to collect something, you will have trouble too. What you'll find is that the tier 1 guys, and this is why I mentioned OpenConfig and SFlow as really good examples that take the industry, I believe, in a direction we want to go, is about the ability to really zoom in on the data I need from this device at this point in time, and moving the device from a poll mode to a push mode. I don't want to sit here and go from one device to another. I actually want the device to tell me when it has something important to say. So we are in transition. That's why I had the slide of the hyperscale guys, because definitely there is stuff to learn from the way they work right now.
Okay, thank you.
Yeah, good presentation.
Thank you.
Good insights and details. Thank you.
I think, Uri, your mic is off.
I forgot. Okay, sorry.
I'm KRS Murthy. What you explained in terms of DTI as an example of implementation, is that limited to a given corporation, whether it's a cell tower company or a telecom company or in other industries within, or is it across the multiple industries? And how do you share what is to be shared, what should not be shared? Would be a very important thing to understand for it to be done in the supply chain, similar, right? Or the industries in a group of industries, and then even at the country level, national level, all of this has to be done. Where is the whole thing happening? Because I do develop national strategies, holistic strategies at the national level. I do M&A, where I'm looking at, when I acquire a cell tower company and take it from 3G or 4G to 5G, I need to kind of understand, at least starting from the holistic level, then down to the detail.
So I would say, first of all, I agree. Second, you are definitely one step ahead of me, because I am really just trying to get some agreement even on the device level. That DTI stuff is about, today, my observation at least is such that what you have is, telemetry is happening here, machine learning or whatever analytics is happening there. There is not even interaction between the two, except for tools like this that would say, let me define an event for you and you report to me when that event is happening. This is saying, can I take it to the next level? Can I actually, because can I kind of get in one location, be it a device in the network, be it a data center, be it whatever is the right granularity for the problem you're trying to solve, you have to distribute the machine learning and collocate it close to the data, because if you are going to try and do this, it's not going to scale. We looked at numbers as an example of the amount of data that could be harvested just from a server platform, what is happening on a network switch, and so on and so forth. This doesn't scale. You don't want to collect all of this. You want to collect the right stuff.
Yeah, and then this, I'm from Bell Labs, we looked at some of these, not AI, today's AI, but older AI version, where you can integrate from end to end, customer premises, exchange network, and the backbone network. How you do that? There is already provisioning data, that's being transmitted at different locations. Not much intelligence yet. Network management, other aspects of it. Also the fail-safe overs and redundancy networks. Quite a lot of the billing, and so where is this?
Are you aware of the efforts happening at MEF and broadband as an example? Because at ENI we are actually working with these groups, and MEF is active as one example of an organization that works on the interface between different operators, different vendors, and they are looking into how they integrate with these technologies. It's going to take a long time for the industry, but all of this work.
Ultimately, one company will know more about the other company than
But
they
that
want
is-
it to be known.
That
Is part of the concern that obviously no operator wants the other guys to understand the problems they are facing and the challenges, etc. So what is the meaningful data that they will be willing to share is by itself a bigger problem.
Okay.
Okay. Any other question? Okay. Thank you.
Thank you, Uri. So now we have some, what is this? Yeah. Okay, we'll do the idea roulette first. Yeah, so how many of you have played the idea roulette before? Oh, well, I apologize for people on the stream. It's a goodbye now. We're going to do things in the room now. Ron, have you turned off the stream? Let's see. Oh, okay. Thank you for joining us and have a good night. So for people in the room, we'll be distributing you 3 cards. Yeah, Michelle will give the cards to you.